Hello everyone, this is our video example related to our lecture where we looked at using tables of values to figure out our specific enthalpies and specific internal energies. This is question 745 from the textbook on page 394. Turn to that, read the question, and follow along with this video example. In this example, we have air at 38 degrees C and 97% relative humidity going into a cooler where it's cooled to 14 degrees C, and it will be fed into a plant area at a rate of 510 meters cubed per minute. So we have our basis there in volumetric flow rate. We are asked to calculate the rate at which water condenses in kilograms per minute. And we are also asked to calculate the cooling requirement in tons. We are assuming that the enthalpy of water vapor is that of saturated steam at the same temperature, and the enthalpy of dry air is given by the expression below. So we are given the enthalpy correlation for bone-dry air in this question. For the water, we're just going to use the tables that we have covered in lecture. So in this question, we're going to do the same thing. We're going to draw the diagram. We're going to figure out what unknowns we have, do a degree of freedom analysis to figure out what tools we have, and verify that we can actually solve this problem. Here we have a cooler in this system. And even though it is not explicitly stated, we're going to assume that the pressure is 1 atmosphere throughout. We have a stream of humid air coming in. We are told that the temperature it comes in at is 38 degrees C, and it has a relative humidity of 97%. It comes out of the cooler at 14 degrees C. I'm going to call this stream 3, and this is stream 2. This is our liquid stream. So as it goes into the cooler, some of the water vapor is going to condense out as a liquid stream, and now we have a stream that is less humid and has a lower temperature. This is 14 degrees C. We are given actually the basis right here as 510 meters cubed per minute. That's our basis in volumetric flow rate. And then we have a liquid stream right here. So that's all we're given in this question. We do have a basis down here, but we're going to do everything in terms of moles, which means we're going to need a molar flow rate down here. And we also know we have two components here, bone-dry air and water. Same thing down here. We have our molar flow rate and our water vapor with our bone-dry air. Down here is all liquid, and we know that bone-dry is not condensable, so we just have the flow rate because we know that this is pure water. We don't need to write any mole fractions associated with this. All right, so here's our diagram. Let's circle our unknowns. And at this point, we really haven't done anything new. This is going to be the same thing as we did with our material balance. But what we have that is new in this case is, for part B, we want to calculate the cooling requirement, which means we're going to have one more unknown, Q, that we can solve for using our energy balance. All right, so let's write out our degree of freedom analysis. We have our 8 unknowns, so 7 from the material part and 1 from energy. So 8 unknowns. The next thing we count is the number of species. That will give us the number of balances we can write. So we have 2 species. We have sum of y equals to 1 in stream 1 and 3. So we have 2 constraints. And now let's look at the number of laws that we have. We have, from our relative humidity, we are able to find our partial pressure, which will allow us to find our mole fraction using Dalton's law. So we have Dalton's law over here. We know that we have vapor-liquid equilibrium for our water between streams 2 and 3. So we have our Raoult's law for water. And we are able to get from V3 to N3 using an ideal gas assumption. So we have our ideal gas law in stream 3. So we have 3 laws. Dalton's law in 1, we have Raoult's law for water, and then we have ideal gas law in stream 3. So those are our 3 laws. So we have 8 minus 2 minus 2 minus 3, that gives us 1, and the last one to calculate Q, that is our new one, which is our energy balance. And that is how we are going to end up with a degree of freedom of 0. We're going to use our 2 species balances, 2 constraints, 3 laws, and the last energy balance to solve for our Q. That will enable us to solve for all of our 8 unknowns. So let's go ahead and do that right now. So here's our diagram, here's our degree of freedom. We're going to go ahead and solve this, and you'll see that the first part, by solving the material balance part, is going to be the exact same thing that we have done in terms of the material balances. So that should be a review. I'm going to go through that really quickly. We're going to solve the ideal gas law, we're going to solve Raoult's law for water, and we're going to use Dalton's law for stream 1. From there, we're going to do our balances, and that should solve the entire problem. That's actually a almost identical example that we have done earlier in this class. So let's go ahead and start with our ideal gas law in 3. We have our volumetric flow rate, we have the temperature and pressure, and so we can just use the ideal gas law to find the molar flow rate in stream 3. Next, we're going to do Raoult's law for water in between streams 2 and 3. Writing out Raoult's law, you can see what this is, but in this case, we only have a single condensable component. So bone-dry air is not condensable, which means the liquid is essentially all water. We don't have to have a mole fraction associated with that. That goes to 1. We can look up our vapor pressure at 14 degrees C from table B3, and that is 11.987 millimeters of mercury. With that, we know P3, we can find our mole fraction of water in the outlet stream. From there, we can use our constraint to find the mole fraction of bone-dry air. All right, so we're done with Raoult's law, we're done with the ideal gas law. Now we have Dalton's law. With Dalton's law, we're given the relative humidity. With the relative humidity, we should be able to find our partial pressure. From the partial pressure, we can find our mole fraction. So the definition of relative humidity is the partial pressure over the vapor pressure at that temperature. And we can look at the vapor pressure up at 38 degrees C from table B3. And we find 49.692 millimeters of mercury. With that, we can find our partial pressure of water in stream 1. Use our Dalton's law to find our mole fraction of water vapor in stream 1. Use our constraint to find that of bone-dry air in stream 1. And now we are almost done with the material balance part. We're just left with our 2 balances. The bone-dry air balance would give us our molar flow rate of the inlet stream, and we find that it's 22.45 kilomoles per minute. Use an overall balance, or you can use the water balance, and we can find actually the amount of condensate, which is 1.09 kilomoles per minute. So at rate at which water condenses, that's what the question is asking for. That is actually the mass, it wants a mass flow rate, so we want M2. We just have to convert N2 to M2 using our molecular weight of water, which is 18 kilograms per kilomole, and we see that we are getting a rate of 19.62 kilograms per minute. So everything so far is, take it as a review, because we have done the exact same thing in our previous examples, looking at ideal gas laws, Dalton's law, and Raoult's law. So now let's go on to what is new for this lecture or this video example, which is our energy balance that will allow us to find Q. In this part, we are asked to calculate the cooling requirements. Essentially, what we are asked to do is to find Q. So let's start with our open system energy balance. We're going to figure out which terms are 0. It's a simple cooler, so there's no shaft work. We're still going to assume kinetic energy and potential energy is negligible for now. At the end, once we have finished solving it, we'll prove that again using some numbers that we have or some assumptions. So what we have is delta H equals to Q, and we can expand out our delta H into sum of all the outputs minus sum of all the inputs. Now, how many outputs and inputs do we have? Based on the drawing that we have 2 outputs, which is our stream 2 and stream 3, and 1 input, which is our stream 1. But we don't have actually only 3 terms, we actually have 5 terms. Because if you think about what is going on here, we are taking the molar flow rate multiplied by the specific enthalpy of the particular species, which means that even though stream 3 we have drawn it as one stream, there are 2 different species in there. What we can find is the specific enthalpy of water vapor in that stream and the specific enthalpy of bone dry air in that stream separately, which means even in that stream, we're going to have two different terms. So we're going to have two terms in stream 3, one term in stream 2, that's just all water, and again, two terms in stream 1. Expanding it out is going to look something like this. This is N2, this is the simple liquid stream at 14 degrees C, and we know it's saturated because it is in equilibrium with the vapor stream. Down here we have our stream 3. We're going to split it up into the water vapor saturated at 14 degrees C, and then here's our bone dry air at 14 degrees C. And the last two terms are our input, which is both from stream 1, the water vapor, and the bone dry air. We already have all the molar flow rates and the mole fractions. We solved for that in our earlier part, in our material balance part. So now what we need to figure out is the 5 different enthalpies at the different temperatures. For the outlet streams of stream 2 and 3 for water, we know that they are in vapor-liquid equilibrium, so we're going to use table B5 for that. So for the liquid stream at 14 degrees C, looked at in table B5, we have 58.8 kilojoules per kilogram. In this case, the question, we are doing everything in terms of moles, so I'm going to convert it to kilojoules per mole using the molecular weight of water, and I have 1.058 kilojoules per mole. We're going to do the same for the vapor stream at 14 degrees C. We know that this is in equilibrium with the liquid stream. We look it up and you see it's 2572.2 kilojoules per kilogram. Convert it, we get 45.49 kilojoules per mole. And now, let's go on to our inlet humid air and look at the water vapor in that stream. We know that it is not saturated because we have a relative humidity that is not 100%. So ideally, we would use table B7 because it is a superheated vapor. But if you look at table B7, at the conditions of 38 degrees C and 1 atmosphere, you will not be able to find, it's not within the range of values. The range of values in table B7 starts at 50 degrees C. So there's nothing below that, so we can't even do any interpolation with the values that's given. What we can do is to make an assumption. We're going to assume that the specific enthalpy of this stream is the same as that of a saturated vapor at the same temperature. So that allows us to use table B5. We will keep the temperature of 38 degrees C, but we'll toss out the pressure. We're going to assume that the effect of pressure is negligible compared to the temperature, and we will actually show that is true when we start to talk about thermodynamic correlations. So what we're going to do is we're going to assume that it's just at 38 degrees C saturated, use table B5, and from there you can see we'll end up with 2570.8 kilojoules per kilogram, and convert it to kilojoules per mole, we have 46.27. All right, so we have the 3 water vapor enthalpies. We need the 2 bone dry air enthalpies. That is actually given in the question. We are given a correlation and equation for that. So we're going to use the correlation for bone dry air. All we need to do is to plug in the temperature at 14 degrees C, and for the outlet, which is the 14 degrees C, we see that the enthalpy is minus 0.3201 kilojoules per mole. What does this negative specific enthalpy means? It means that the specific enthalpy is lower than that of the reference state. So what is the reference state of bone dry air from this equation? I know it is 25 degrees C because that is the temperature at which I'm going to get a specific enthalpy of 0. We're going to redo this for our 38 degrees C, that's our inlet stream, and we end up with our specific enthalpy here. Now we have all the values that we need. We can put it all into this equation. You could just start to substitute all the numbers that you have in here, but the neater way to present this in a more systematic way is to just really come up with a table. And this will be a lot more important once we start to do thermodynamic correlations and having to create hypothetical paths. But for now, this is just a neat way to look at what's going on. We have our species, we have our inputs and our outputs, the molar flow rates, and the specific enthalpies. We don't have any liquid water coming in. We have water in vapor form and bone dry air coming in. And coming out, we have all 3 of them. So by presenting it in this way, we know that Q is essentially the sum of multiplying these 2 plus these 2 plus these 2, and then we'll subtract the summation of the product of these 2 terms. So with that, we can put in the numbers, crunch the numbers into our calculator. We end up with a unit of kilojoules per minute. do the proper conversions, we want this in tons, so we can convert it to tons and we get minus 268 tons. What the minus sign means is that we are losing heat to the surroundings. The system is losing heat, which should make sense because this is a cooler. So we're essentially losing heat to the surroundings. All right, so now let's test the assumption that our delta EK is approximately 0. And we'll move on to our delta EP, the potential energy after that. We have always made this assumption. Let's confirm that this is indeed true. So we know we have half mu squared. We need the mass flow rates of our outlet and our inlet stream. So to do that, we actually need the volumetric flow rates and the cross-sectional area of the pipe that will allow us to find our velocities, U1 and U3. You'll see that I actually ignored U2, which is the liquid stream. Think about your air conditioner or your dehumidifier. The water essentially just drips into a bucket. It doesn't actually flow at a very significant flow rate. So we're just going to assume that the kinetic energy of that stream is just 0. So we're just going to look at the vapor streams here. To get our U, we need our volumetric flow rates. We have a basis for our stream 3, so we already have the volumetric flow rate. For our stream 1, we have the molar flow rate that we calculated. So we're going to use our ideal gas law to convert it to a volumetric flow rate. What we're going to do now is just assume that the inlet and outlet pipes have the same cross-sectional area. We're not actually going to give it some value. We're just going to assume that it's the same cross-sectional area. And that what it allows us to do is to relate our velocities in stream 1 and stream 3. By taking the ratios, you can see that the A's are just going to cancel. So the ratios of the velocities is the same as the ratio of the volumetric flow rate. And now we have a correlation that relates our velocity, outlet velocity versus our inlet velocity. We have our velocities. The last thing we need is our mass flow rates. We have our volumetric flow rates. Actually, we have our molar flow rates in both cases. So all we need to do is to use the molecular weight of that stream. Now you will realize that in both streams we have water and bone-dry air. But in this case, we're not actually doing an actual calculation. We don't need the actual numbers. We're just trying to show that delta EK is approximately 0. So rather than weighing the molecular weights, which you can do for bone-dry air and water to find the actual molecular weight of that stream, I am just going to use the molecular weight of bone-dry air because there's a lot more bone-dry air than water vapor. The mole fractions are generally more than 90% of bone-dry air. So just for a quick estimate, I'm just using the molecular weight of bone-dry air, find the mass flow rate of stream 1, do the same for stream 3, and now I have everything I can put into my equation for my change in kinetic energy. Here's my change in kinetic energy, outlet minus the inlet. We have our velocities in terms of U1, so I'm going to make that substitution and simplify it, and we have minus 1.335 U1 squared. Doing everything in SI units, I know my U1 will be in meters per second. All right, so this is the expression for our change in kinetic energy. And I'm just repeating here because we're going to use it. So when is this going to be significant? Let's assume that we know our Q, we know the magnitude of our heat transfer. So assume that the magnitude of this change in kinetic energy is at least 10% of Q for our delta EK to even be significant. So we want the magnitude of our change in kinetic energy to be at least 10% of our heat transfer. We know the value from, as we have calculated earlier in this question. And that brings us to about 106.7 times 10 to the power 3 joules per second. This will allow us to solve for a velocity that will give us this magnitude of change in kinetic energy. We know the magnitude is 1.335 U1 squared. Now we can solve for U1. U1 is 283 meters per second. This is the velocity for the input stream that will make our change in kinetic energy 10% of the Q that we calculated. And that's when we can assume that this is at least significant enough for us to include this term. As a source of comparison, how fast is 283 meters per second? So this is from engineeringtoolbox.com, and some of the common applications you might have seen in your house or in school. Ventilation ducts, or in the winter when you have your warm air going, that's about 1 to 5 meters per second of airflow. When you use your vacuum cleaner, it starts to get really loud, and that's about 8 to 15 meters per second. If you have worked at a chemical plant and you have been in a compressed air room, I have actually worked on a compressed air compressor before, and we actually have to wear earplugs going into it just for as with regulation. That's 20 to 30 meters per second. So even with that, we are still only a fraction of this 283 meters per second that we are looking at here. As another comparison, when you drive down the highway at 70 miles per hour, you are going at about just over 30 meters per second. So 283 meters per second is really, really, really fast and not practical in terms of airflow that we are looking at. If we assume just an airflow a velocity of 5 meters per second, we can calculate our delta EK term. We see that it's 33.38 joules per second. Compare that with our Q, it is less than 1% of our Q. And that's why, in general, we can assume that the kinetic energy term is 0. Even though there is some magnitude associated with it, the other terms are just going to swamp that out. Let's do the same analysis with our potential energy. So we might have our inlet pipe and our outlet pipe at different elevations. What is the change in elevation that's needed for that term to actually be significant? We're going to set the reference plane as our inlet elevation, so that makes our calculations a little easier. Do the same analysis. We're going to say that the change in potential energy is significant if it is about 10% or at least 10% of our Q. So that's the same value down there. Expand out our change in potential energy is the mgz of the outlet minus the mgz of the inlet. We have set the inlet to be 0, so that's easy. With that, we can calculate our Z3, which is our delta Z. And we see that between our inlet and outlet pipes, it has to be 1.05 kilometers for our change in potential energy to be 10% of what we calculated for our Q term. And so this is, again, impractical for that to, we won't have a cooler that's going to be a kilometer in height. So that's the distance between the inlet and outlet pipes. So in general, what you're going to see is we have always in the past assumed delta EK, delta EP to be 0, and that is generally a very good assumption when we have chemical process units that have a change in temperature, change in phase, or change in composition, such that we have some delta H or Q or shaft work. This potential energy change and kinetic energy change are going to be swamped out by those terms. So usually those will be 0. When are these not considered 0? This will be when we have no change in temperature, no phase changes, no change in composition, and the most common one you're going to see is just simple fluid flow in pipes, where we are not changing the temperature or we are not doing any reactions to it. This is actually what we call mechanical energy balances. There's a section in the textbook that talks about this, section 7.7, where it actually derives Bernoulli's equation. We're not actually going to go through this portion in this class because for most of you, you're going to take fluid mechanics somewhere along in your chemical engineering curriculum, and part of fluid mechanics, we're going to spend a lot of time in Bernoulli's equation. So we're just going to leave that for that class. So that's all we have for this video example. Work hard, be smart. I will see you next time.